Welcome, everyone. Right now, in some of the most advanced laboratories across the globe, scientists are conducting experiments that could completely change our understanding of reality. These experiments have led to discoveries hidden deep within the realms of quantum mechanics and the mathematics of black holes, and they suggest something truly extraordinary. Our universe might not be what we think it is. The stars, the planets, even the very body you inhabit, could be much stranger than we ever imagined. A projection, a hologram, or perhaps even a simulation. This might sound far-fetched, but these ideas aren't pulled from science fiction. They are based on groundbreaking theories in modern physics that challenge our perception of the world around us. So if you're ready to dive into one of the deepest mysteries of science, stick with me. You'll want to hear where this goes, as it might change everything you thought you knew about the nature of the universe. Let's begin. Back in 1974, Stephen Hawking made a discovery that sent shockwaves through the scientific community. He showed that black holes are not permanent, as was previously thought. Instead, they slowly leak radiation and eventually evaporate. While this sounds like a small detail, it led to a monumental problem that has puzzled physicists ever since. Here's why it matters. Everything in our universe, as we understand it, follows one fundamental rule. Information cannot be destroyed. If you burn a book, for example, the information it contained isn't truly gone. It's still there, embedded in the smoke, the ash, the heat, and even in the space around it. Physics demands that no information be lost in the universe. It must always be preserved. However, black holes seem to violate this principle. When matter falls into a black hole, it seems to disappear behind the event horizon, the boundary beyond which nothing can escape. The mystery deepens because, when black holes eventually evaporate due to Hawking radiation, the radiation itself carries no information about the matter that once existed inside the black hole. The information appears to vanish, which presents a contradiction between two pillars of modern physics. Einstein's theory of general relativity says that this loss of information is fine, but quantum mechanics, which governs the behavior of particles at the smallest scales, insists that this is impossible. In other words, two of the most successful theories in physics were in direct conflict, and one of them had to be wrong. This paradox led physicists to search for a resolution. What they uncovered, however, was even stranger than anyone anticipated. In 1993, Dutch physicist Gerard 't Hooft proposed an audacious idea. What if the information inside a black hole doesn't actually fall into it? Instead, he suggested that the information could remain on the surface of the black hole, encoded on its event horizon, much like data stored on a computer's hard drive. This hypothesis gained more traction when Leonard Susskind further developed it. He showed that, instead of disappearing into the black hole, everything inside could be described by the information encoded on the event horizon. This idea became a cornerstone of modern physics, and it has since been confirmed by experiments. It's a radical theory, but it makes sense within the framework of quantum mechanics. However, here's the part that could shake everything to its core. If this principle applies to black holes, what if it applies to the entire universe as well? Imagine for a moment that everything you see around you, your body, the stars above, the vast expanse of space itself, is not what it seems. What if all of it is nothing more than information encoded on a distant surface, billions of miles away? We are taught to think of ourselves as living in 3 dimensions, moving through real, solid space. But what if this space is an illusion, and what we experience as reality is merely a projection of data? This isn't a wild guess or science fiction. It's called the holographic principle, a leading theory in theoretical physics, which has gained considerable attention among scientists. In fact, computer simulations have even been run to test this idea. One of the most striking confirmations of this theory came in 2013 when Japanese physicist Yoshifumi Hyakutake used string theory to calculate the internal energy of a black hole. He then compared it to the energy of a universe with fewer dimensions, one that lacked gravity. The two numbers matched perfectly. This wasn't a coincidence. It was proof that lower-dimensional universes could theoretically explain the physics of our own universe, and it provided additional weight to the idea that we may be living in a projection. As the research progressed, it became clear that the holographic principle wasn't just a theoretical idea. It was supported by real-world observations. In fact, there were strange patterns in the universe that seemed to make sense only if reality were holographic. These patterns have been found in areas like the cosmic microwave background radiation, which is the afterglow of the Big Bang. In 2017, a team of scientists published their findings after analyzing these irregularities in the cosmic microwave background. They discovered that the patterns closely matched predictions made by holographic models, as well as the predictions from the standard cosmological models. This didn't immediately prove the universe was holographic, but it showed that the holographic models could explain the data just as well as the more traditional theories. Still, the idea of a holographic universe challenges everything we know about space and time. According to this theory, what we perceive as three-dimensional space is actually a projection from a distant two-dimensional surface, billions of light-years away. Our entire existence, everything we touch and see, could be nothing more than information encoded on this distant boundary. This theory has gained traction because it provides a neat solution to a number of puzzles in physics. For one, it resolves the black hole information paradox, something that has baffled physicists for decades. If the universe is a hologram, space itself may not be fundamental. The distances between objects, like the gap between you and the nearest star, could be an illusion. It would mean that space, as we understand it, might not even exist in the way we think. In essence, the holographic principle suggests that everything we experience, our world, our thoughts, our interactions, is a projection of data that exists somewhere else. It's like watching a movie. The characters seem to move through a three-dimensional world, but in reality, all of that information exists on a flat screen. The depth of the movie is an illusion, and so too might the depth of our reality. This principle is part of a larger body of work that emerged from string theory in the late 1990s. The central idea is that all of reality, including the forces that govern the universe, might emerge from simpler, lower-dimensional information. In 1997, physicist Juan Maldacena made a groundbreaking discovery in theoretical physics. He showed that a five-dimensional universe with gravity could describe the same physics as a four-dimensional universe without gravity. The two universes appeared completely different, but their underlying physics were identical. This idea, known as the ADS-CFT correspondence, was a huge breakthrough in our understanding of space and time. Maldacena's discovery is one of the cornerstones of the holographic principle. It showed that different, seemingly unrelated realities could be mathematically equivalent. This opened up new ways of thinking about the universe and the nature of reality. But it also led to more questions. If our universe is holographic, then what exactly is real? What does this mean for the way we perceive space and time? Physicists have continued to test these ideas with computer simulations and real-world experiments. In 2013, researchers used string theory to calculate the energy of a black hole and compared it to the energy of a simpler, lower-dimensional universe. The numbers matched perfectly, adding weight to the holographic hypothesis. But even as the math worked out, there was still the unsettling realization that if the universe is holographic, it could mean that space and time as we know them are not fundamental. The idea of a holographic universe isn't new. It's been proposed in various forms over the years, but recent research has given it new credibility. In fact, some of the most important breakthroughs in physics, including studies of black holes and quantum mechanics, are now seen through the lens of the holographic principle. And as more evidence mounts, it's becoming harder to ignore. This is where things get even more mind-bending. If our universe is a hologram, what does that mean for the laws of physics? If space itself is an illusion, does this mean that the fundamental constants of nature, like the speed of light or the gravitational constant, are just artifacts of the holographic projection? These questions lead us to even more profound implications about the nature of reality. To further explore this idea, scientists have begun to look for evidence that the universe might indeed be a hologram. One of the most intriguing pieces of evidence comes from the study of cosmic rays. These high-energy particles, which travel across the universe at nearly the speed of light, could provide crucial clues about the nature of space itself. If the universe is a hologram, then these particles might behave differently than we expect. In particular, scientists have been looking for signs that the universe is not infinitely smooth, but instead has a sort of pixelated structure. This idea comes from a concept known as digital physics, which suggests that the universe is a computational system. If space is discrete, like pixels on a screen, then certain high-energy particles should show subtle irregularities in their behavior, such as directional preferences or anomalies in their trajectories. So far, experiments haven't provided definitive evidence of this, but the search is ongoing. The most sensitive instruments, like the GEO 600 gravitational wave detector in Germany, have detected strange patterns in space-time. These patterns don't appear to be caused by mechanical vibrations or other known sources of interference. Instead, they look like the kinds of fluctuations that might be expected if the universe is holographic, a graininess, or holographic noise that would indicate a limit to the resolution of space and time. This noise is extremely faint, but it is significant enough to catch the attention of physicists. If these signals are real, it would be the first direct evidence of the universe's pixelated nature. It would show that space-time, rather than being a smooth, continuous fabric, is actually made up of discrete units. Just like pixels on a screen, these units could be the building blocks of our reality, and the noise might be the static that emerges when the universe reaches its computational limit. Other experiments, including those using gravitational wave detectors like LIGO, are continuing to look for similar anomalies. While they haven't yet found the definitive evidence that would prove the universe is holographic, the presence of this strange noise in the data is a strong indication that something unexpected is happening. As our technology improves, it's possible that we will be able to detect these glitches with greater precision, confirming the holographic theory once and for all. However, this is not the only piece of evidence that points toward the universe being a simulation. Another line of inquiry comes from the study of quantum mechanics, particularly the phenomenon of quantum entanglement. This strange and counterintuitive behavior occurs when two particles become linked in such a way that their properties are intertwined, even when they are separated by vast distances. Quantum entanglement defies the laws of classical physics, which say that information cannot travel faster than the speed of light. Yet, when two entangled particles are measured, the measurement of one particle instantly affects the other, no matter how far apart they are. This has been confirmed by experiments, and it has left scientists scratching their heads, trying to understand how information can travel faster than light. One possible explanation comes from the idea that these particles aren't really separate entities at all. Instead, they might be two parts of the same underlying information, just like the pixels on a screen. If space-time itself is holographic, then these entangled particles could be linked by the same data that forms the projection of our universe. The apparent instantaneous communication between them could be the result of them sharing the same underlying information, much like two pieces of code that reference the same memory address in a computer program. This theory fits with what we know about how quantum entanglement works. If space and time are not fundamental but are instead emergent properties of underlying data, then the concept of entanglement makes perfect sense. It would also explain why entangled particles seem to violate the laws of physics. They're not communicating across space as we understand it. Instead, they're accessing the same underlying data. In fact, some physicists, including Mark van Ramden, believe that quantum entanglement is essential for the very existence of space-time itself. According to this idea, space is not a pre-existing backdrop for the universe. Rather, it emerges from the entanglement patterns between particles. This would mean that the fabric of space-time is not fundamental. It's a construct that arises from the information encoded in the holographic projection of the universe. Another compelling aspect of this theory is the so-called mathematical universe hypothesis proposed by physicist Max Tegmark. According to Tegmark, the universe is not merely described by mathematics, It is mathematics. He suggests that the structure of the universe, the laws of physics, and everything we experience are all part of a mathematical framework. In this view, reality is not something that exists independently of our minds. Instead, it is a product of mathematical structures that exist in a higher dimensional space. Tegmark's theory offers a fascinating perspective on why the universe appears to follow such precise mathematical laws. From the speed of light to the gravitational constant, the fundamental constants of nature are strikingly consistent and unchanging. This precision can be seen as a result of the universe being based on a higher-order mathematical structure. If the universe is, in fact, a mathematical entity, then it could explain why the laws of physics are so finely tuned to support life. These laws may not be discovered, but rather unveiled as we learn to understand the underlying mathematical structure. This also ties in with the holographic model. If the universe is fundamentally mathematical, then the physical world we experience might be an illusion, much like a virtual reality simulation. In this case, everything we experience, our physical sensations, our perception of space and time, could be a representation of mathematical relationships that exist in a higher dimensional framework. This idea might sound abstract, but it provides a coherent explanation for the strange and counterintuitive behaviors of particles and forces that we observe in quantum mechanics. What makes this even more fascinating is that some of the greatest minds in physics, like Stephen Hawking and Brian Greene, have suggested that the ultimate theory of everything will be written in the language of mathematics. If reality is fundamentally mathematical, then the universe itself could be understood as a computation, a vast calculation unfolding in real time. This would also explain why we find mathematical patterns everywhere in nature. From the spirals in seashells to the shape of galaxies, nature seems to follow mathematical rules. If the universe is a giant computation, this would be expected, as the universe would be following a set of instructions, much like a computer executing a program. This ties back to the holographic principle, which suggests that everything in the universe is encoded on a distant boundary, much like a hologram. If the universe is fundamentally mathematical, then the projection of this data could create the illusion of the three-dimensional world we experience. In essence, the universe could be a vast, self-contained mathematical system that exists in a higher dimensional space, and we are merely experiencing a two-dimensional projection of that data. As we explore these ideas, the boundaries between physics, mathematics, and philosophy begin to blur. If the universe is a mathematical entity, then the question arises, what is the nature of the observer within this system? Are we real, or are we just part of the illusion created by the mathematical framework? This brings us to the simulation hypothesis, which suggests that our entire existence could be a simulation created by a more advanced civilization. The simulation hypothesis, proposed by philosopher Nick Bostrom, suggests that there is a high probability that we are living in a computer-generated reality. According to Bostrom, if advanced civilizations are capable of creating highly sophisticated simulations, then the chances are that we are living in one of these simulations, rather than in what we traditionally think of as real reality. He argues that at least one of the following statements must be true. Human civilization will go extinct before reaching a level of technological sophistication where we could create realistic simulations of conscious beings. Advanced civilizations capable of creating such simulations are not interested. In doing so, we are almost certainly living in a simulation. Bostrom's argument hinges on the assumption that if future civilizations are capable of creating simulations that are indistinguishable from reality, then the number of simulated realities would vastly outnumber the single base reality. If that's the case, then the probability that we are living in the base reality is incredibly small. The sheer number of simulated worlds would make it much more likely that we are living in one of them. The idea is that as computing power advances, future civilizations could create simulations so realistic that the conscious beings inside them wouldn't be able to tell that they were inside a simulation. These simulated worlds could be so complex and detailed that they would perfectly mimic our current reality. In fact, they would be so indistinguishable from reality that the beings within the simulation would have no way of knowing they were not in the real world. In a sense, this theory is an extension of the holographic principle. If our universe is a simulation, then the data that defines our world would be encoded in some higher dimensional space, just as in the holographic model. The difference is that instead of being a natural part of the universe, the simulation hypothesis suggests that our reality is artificially constructed by an advanced civilization, potentially using vast amounts of computing power to create a simulation so sophisticated that we can't perceive its true nature. This raises interesting philosophical questions about the nature of consciousness and reality. If we are living in a simulation, does that mean that our consciousness is somehow programmed by the simulation's creators? Are we aware of ourselves only because the simulation is designed to give us the illusion of consciousness? These questions challenge our traditional views of what it means to be alive and what it means to be conscious. Interestingly, some of the most famous figures in technology and science have expressed interest in the simulation hypothesis. Elon Musk, for example, has publicly stated that he believes the odds are high that we are living in a simulation. Musk argues that if we look at the rapid development of virtual reality and video games, it's not unreasonable to think that future civilizations will be able to create simulations indistinguishable from reality. He points out that, based on the progression of technology, it's not a matter of if we will be able to create simulations, but rather when. Musk's view aligns with Bostrom's argument that as computing power advances, simulations will become more and more sophisticated, making it increasingly likely that we are living in one. If future civilizations are capable of creating these realistic simulations, it stands to reason that there could be billions of simulated worlds, all existing within a larger, simulated reality. The idea that we might be living in a simulation raises some profound questions about the nature of reality and existence. If our universe is indeed a simulation, then what does that mean for the laws of physics? Are the fundamental constants, like the speed of light and the gravitational constant, real, or are they simply part of the program's code? If the universe is a simulation, then everything we experience, from the smallest particles to the vastness of space, could be a set of instructions being processed by a supercomputer somewhere in a higher dimensional space. This leads to an even more intriguing possibility. The idea that our universe is not just a simulation, but a highly optimized one. In the same way that computer programs are designed to run efficiently, the universe we experience might be a simulation created with computational efficiency in mind. This could mean that the universe is designed to minimize the computational resources required to simulate it. For example, phenomena that we perceive as constants in nature, like the speed of light, could be fixed values chosen to optimize the simulation's processing power. In fact, some scientists and computer theorists suggest that the universe might be computationally efficient in ways we don't fully understand. For example, the fine-tuning of the universe, the fact that certain physical constants are precisely set to allow for the existence of life, might be the result of deliberate optimization. If the universe were a simulation, the constants that govern it could be set in a way that minimizes the complexity of the simulation, ensuring that it runs smoothly and efficiently. This concept is not just speculative. Some researchers have proposed that we might be able to detect glitches or inefficiencies in the simulation that would provide evidence of its artificial nature. Just as video games can have glitches or bugs in their programming, the universe might show subtle signs that it's a simulated reality. These glitches could appear as anomalies in the laws of physics or unexpected behaviors in the way particles interact. If these glitches are discovered, it could provide the first direct evidence that we are living in a simulation. One example of a potential glitch could come from the study of quantum mechanics. As we've seen in experiments like the double-slit experiment, particles behave in ways that defy classical physics, appearing to be in multiple states at once or instantly influencing each other across vast distances. These strange behaviors could be the result of limitations in the simulation's processing power. suggesting that the reality we experience is not as solid and deterministic as it seems. In fact, some scientists believe that the apparent randomness of quantum mechanics might be a sign of a computational limitation. If the universe is a simulation, the behavior of particles could be governed by probabilistic rules, similar to how a computer might generate random numbers when simulating a system. This could explain why quantum mechanics behaves in ways that seem illogical or unpredictable. If the simulation is running at its maximum capacity, it might resort to randomness to save on computational resources, rather than simulating every possible outcome with perfect precision. As our understanding of quantum mechanics deepens, we may find more evidence that the universe operates in a way that suggests it is a simulation. The development of new technologies, like quantum computers, could give us the tools to test these theories and potentially uncover flaws or limitations in the simulation's design. If such flaws are detected, it could mark the beginning of a new era in physics, where the idea of the universe as a simulation is no longer just a theory, but a testable hypothesis. If the universe is indeed a simulation, then what are the implications for our understanding of consciousness and existence? Consciousness itself has long been one of the most mysterious aspects of reality. Despite years of research, we still don't fully understand how subjective experience arises from physical processes in the brain. But if we are living in a simulation, then consciousness might not be the result of biological processes at all. Instead, it could be a byproduct of the simulation's design, an emergent property that arises from the data being processed by the system. In this view, consciousness could be something akin to the artificial intelligence within the simulation. Just as we create AI to mimic human-like behavior, the simulation could have programmed us to experience self-awareness. This would mean that our consciousness isn't an inherent property of the universe. Instead, it's a feature of the simulation's program. This idea raises fundamental questions about what it means to be alive and aware. If we are living in a simulation, is our sense of self real, or is it merely an illusion created by the simulation's code? This concept also brings up the question of the nature of free will. If the universe is a simulation, then every action we take, every decision we make, could be part of the simulation's design. Our sense of free will might be just as illusory as the space and time we perceive around us. In this scenario, our actions would still feel real to us, but they would be predetermined by the parameters set by the creators of the simulation. This doesn't necessarily mean that we're programmed in the traditional sense. Instead, it could mean that our choices are the result of complex algorithms designed to give us the appearance of free will. Some scientists have proposed that the very idea of free will is an illusion created by the brain to help us make decisions and navigate the world. In a simulation, this illusion could be even more pronounced. The simulation could be designed in such a way that we believe we are making choices, but in reality, those choices might be the result of the underlying structure of the program. This raises profound philosophical questions about responsibility, ethics, and the nature of our actions. If we are living in a simulation, can we still be held accountable for our decisions? The question of whether we can ever escape the simulation is another fascinating topic. If we are indeed trapped in a simulated reality, is there any way to break out of it? Some theories suggest that if we can somehow gain access to the underlying hardware of the simulation, we might be able to free ourselves from it. However, the creators of the simulation would likely have set up barriers to prevent this. Just as the characters in a video game are unaware of the system that runs the game, we might be unable to perceive the true nature of our reality. Even if we were to discover that we are in a simulation, how could we possibly escape it without the knowledge and tools to do so? In the end, the possibility that we are living in a simulation raises more questions than answers. It challenges everything we know about the nature of reality, consciousness, and free will. It forces us to reconsider our understanding of the universe and our place within it. And while we may never have definitive proof that we are living in a simulation, the idea that our reality could be artificially constructed opens up new avenues for scientific exploration and philosophical inquiry. As we continue to push the boundaries of science and technology, It's possible that we may one day uncover the truth about the nature of our existence. As we explore these profound ideas, the question remains, how can we test the simulation hypothesis? How can we prove that our universe is a hologram or a simulation? One possibility lies in the search for anomalies, or glitches in the fabric of reality. If our universe is indeed a simulation, there may be imperfections in the system, unexplained anomalies that hint at the artificial nature of our existence. These glitches could manifest in various ways, such as irregularities in the laws of physics, inconsistencies in the behavior of particles, or discrepancies in the cosmic background radiation. One of the most promising areas of research is the study of quantum mechanics. As we've seen, quantum entanglement and other strange phenomena suggest that the universe behaves in ways that are difficult to reconcile with classical physics. Some scientists believe that these behaviors could be a result of the limitations of the simulation itself. If the simulation is running at its computational limits, it might resort to randomness or uncertainty in order to conserve processing power. This could explain why particles behave unpredictably, or why certain physical laws seem to break down under extreme conditions. Another avenue for testing the simulation hypothesis is through the study of cosmic rays. These high-energy particles, which travel across the universe at nearly the speed of light, could provide clues about the nature of space-time. If the universe is a simulation, these particles might behave differently than we expect. For example, scientists have speculated that cosmic rays might show signs of pixelation, subtle irregularities that would suggest a discrete structure underlying space-time. This could be the equivalent of seeing the pixels in a computer-generated image, offering the first tangible evidence that our universe is a simulated reality. Despite these potential clues, the idea that we are living in a simulation remains speculative. While it's a fascinating theory, it's important to remember that there is currently no concrete evidence to prove that our reality is artificial. However, the more we learn about the nature of space, time, and quantum mechanics, the more we may be able to test the simulation hypothesis. As our understanding of the universe deepens, we may find new ways to probe the limits of reality and uncover the truth about the world we live in. In the end, the possibility that our universe is a simulation challenges the very foundation of science and philosophy. It forces us to rethink our assumptions about reality, consciousness, and existence itself. Whether or not we are living in a simulation, the questions raised by this hypothesis will continue to inspire curiosity and exploration for years to come. As we continue to push the boundaries of knowledge, the search for the truth about our existence will remain one of the most profound and exciting quests in science.